Good morning to everybody. It's a real pleasure to be here. Last time I've been here was, I think, 7 years ago. So today I will talk about automotive radar and try to give you a little bit of an holistic view about the developments in the field towards autonomous driving. Before I get to the main content of my presentation, I want to give you a little bit of a small intro of what NXP is. NXP Semiconductors is a company with a very old heritage. We focus on four main areas. It's a company that focuses on the edge markets: automotive, industrial, IoT, mobile, and communications infrastructure. We have a very global footprint. It's a company of 31,000 people on 30 different countries around the world, combining basically the heritage of Philips, becoming NXP, and since 2019 also Freescale, that was Motorola, merged in one company called the new NXP. So today we'll talk about the automotive part, where NXP is having a very active role. The whole automotive field is emerging. 10 years ago, it was a very boring field to work on. I would actually not want to work there. But then automotive radar came in and many other very interesting developments. Today, it is an exciting field to work on. There is many different types of applications. And you have to realize that an average vehicle today basically has approximately 1,000 semiconductor chips. And this is only increasing. So the relative value of the semiconductor industry has in a car is been changing and increasing substantially. So we're going to talk about ADAS, so autonomous driving assistance systems and automotive radar trends, specifically for the transceiver front end. I will give you a little bit of an introduction on the basic radar principles so that you can navigate yourself into the complexity of the field, especially moving towards high resolution, which is a key word and a key element for future systems. And then enabling technologies on circuit antenna and sensor, and also have a look a little bit what's coming up towards higher frequencies. Before I move on to the main content, I would like to simply steer you up a little bit with a small video that we made with a colleague of mine. So if we can actually play the video.
Imaging radar is important today because it's a new key technology for building safer cars. It allows the vehicle to travel in conditions where lighting is poor or the driver has a hard time seeing, so hard rain, light rain, fog. Cases where the driver can't see well, the radar can still see, and then from that to make the safest driving decisions that's possible. Autonomous vehicles are definitely in our future, and they will become the norm when they become extremely safe. We need sensors to continue to mature, and one of the key sensors is imaging radar.
Hi, I'm Robert Carter, Field Applications Engineer for NXP Semiconductors. Today I would like to introduce you to a new imaging radar sensor that we have mounted to our vehicle. This sensor is powered by an NXP radar chipset, and it's developed by our partner Cubtech. Our chipset consists of an S32R45 radar processor and the industry's first dedicated 16 nanometer imaging radar processor. These processors deliver unparalleled computation power for highly efficient real-time data processing at low power dissipation. To provide data for the digital signal processor, there are 4 cascaded RF CMOS TEF 8200 radar transceivers. These transceivers provide 2 times RF performance improvement for enhanced sensing. 4D imaging radar refers to a radar that measures 4 key parameters of objects that the radar can see in its field of view. The first one is range, or distance between the radar and the object. The sensor in our case is actually detecting short range and long range simultaneously. This capability is due to a sophisticated antenna working with the hardware acceleration on our processor, which provides the processing power to process different modes simultaneously. One of the next things that is measured is the velocity or speed of the object. The radar can determine the difference in velocity between the vehicle and the object. This information is critical, for example, when executing automatic emergency braking, performing adaptive cruise control, or for making safe driving decisions associated with route planning. Another key parameter that is measured is azimuth angle. This measurement describes how far to the right or to the left a detected object lies from the center line of the radar. When multiple objects are in close proximity to one another, imaging radar provides sub-1 degree azimuth resolution so that these objects can be separated from one another. The final dimension is elevation angle. This is a measurement which allows the radar to calculate the height of an object above the road surface. The radar can determine if objects it detects are safe to travel over or if they need to be avoided. One key use case for this parameter in an imaging radar involves detecting an overpass or bridge structure over the roadway while at the same time detecting if the roadway beneath the structure is clear for safe travel. All four dimensions taken together allow the radar to expertly map the scene in front of it. This information can then be used to alert the driver of the vehicle so safe driving decisions can be made. Today, NXP has a leading position in automotive radar. Through our continuous innovation in millimeter wave design, radar signal processing, and advanced algorithms, we will continue to develop products that will keep us in an industry-leading position for years to come.
All right, so by the end of the presentation, you will understand a bit more about the technology behind those imaging radars. So let's start building up this story. So as I mentioned earlier, the automotive landscape is really changing. So today's cars or future cars are more like robots on four wheels rather than, you know, the four wheels with a metal weld type of industry behind it. So there are three pillars of innovation. One is relating to the Vision Zero. Vision Zero means zero road fatalities. And there is statistics indicating that 90% of the cases of road accidents relate to human error. So that needs to be taken out of the equation. The second topic relates to the electric evolution. This drives to zero emissions, the whole green energy discussion, and you see that actually changing rapidly around us with electric cars and the whole system that supports it. The third one is upgradable future. Practically, we're talking about a vision to software-defined vehicles. This is how the OEMs today are describing this transformation. The last thing you want is that you have to upgrade your car every time you go back home. There's so much sophisticated electronics in the car, you simply want to experience something that you don't see practically. It's happening as you ride, it's happening as you stop, and everything is actually working. And all the software is decoupled from the hardware in the car. To satisfy this vision, basically, the OEMs today are changing drastically the vehicle architecture. So on the left side here, you see today's systems that are based on a sort of a flat hierarchy. The whole networking in the car is flat, and on a flat architecture, you can think of a harness that actually weighs up to 50 or 60 kilos of cable in a modern, expensive car. That's a lot of weight. And of course, there is no connection between the different sensors or different domains. So that brings basically the industry to move into the domain-based architecture. So we have a central gateway and the different type of applications or domains like connectivity, body and comfort, powertrain, and ADAS specifically. This is a transformer intermediate step to move into the full zonal architectures where everything happens in a central processor, high-performance computing, automotive standards in the middle, where all the fusion is taken there, all the information from everywhere around the car, be that from your audio system recognizing a siren moving into your imaging radars or anything else coming and being processed in a central. So that's the user-defined car of the future. Looking at the autonomous driving, the industry has set a few standards, 5 levels of automation. Practically, there are 6. Level 0 is the one that you have no automation, but level 1 is the reality today. So on the top, you see an evolving bubble around the car, which is the active safety around the car. The car sees around it in different ranges, different things. So today, level 1 deals about basic emergency actions, lane keeping, adaptive cruise control. And on the far right is the future where mind's free, hands free. There is actually no wheel, steering wheel. There is nothing you need to worry about. And in between, there is this very interesting level 2+, where the industry realized how much complex it is to move to level 2 and 3. So they introduced a level 2+, where also all the legal aspects on who has responsibility, many other technological things are being addressed. Now, to come to autonomous, full autonomy in driving, we need the redundancy of sensors. There is no single sensor that can make it happen. Different sensors are good at different things. So you have, for example, a camera that is able to detect colors, but you cannot detect depth or distance. You have a LiDAR that actually is very precise, but it lacks the velocity capability. And you have radar that actually can give you the velocity capability, can give you the bad weather performance, but it lacks the resolution. So all this combined together into what we call fusion of sensors is the way basically to move forward in autonomous driving. That's redundancy at the sensor modality level. We will focus on radar, mentioning only that the key trend in LiDAR, this is an emerging technology that will come up, is how to reduce the complexity of a sensor that you might see on these Velodyne type of Google cars, that big boxes like this, into something that can fit in the car in a sort of a sub $100 price per unit. That's the big challenge there. So automotive radar. Well, some people tried that before. It's an interesting idea, but that's not what the real thing is about. So how it looks today? Today, we're in a phase where some leading OEM manufacturers will introduce the level 3 cars on their flagship products, where they use multiple different sensors, as I said, LiDAR, camera sensors, many of them around. This is Mercedes and this is BMW. And this is where we're standing today. And it's important to realize that the aesthetics of the car play a really, really important role on the adoption of sensors. You cannot just have a sensor sticking out of the car. It just has to be small and be embedded into the car, and that brings additional complexity. Typical example is the bumper reflection. Your radar behind the bumper, it just hits the bumper, gets all the self-reflections, and creates major difficulties in dynamic range and things like that. There are several different situations or use cases, we call them, where a car actually, or the radars of the car will be optimized for. So blind spot detection, lane change assist, cross-traffic alert, so you're having a parking, you're getting out of the parking and there is, people walking or another car. Adaptive cruise control for highways, the safety bubble, the cocoon as we call it, and the emergency braking. So these are typical cases. But there are two cases specifically that currently are at the epicenter of attention for the next generation radars. And these are, on the left, OEMs have the need at the moment to put to us, we're a tier 2, making the chips, not the sensor. Sensor is made by tier 1s, where you need to provide a system that is able to detect a very small object, such as a motorcycle, and also a vulnerable object next to a big truck at a very long distance. Think about 300 meters, 400 meters. And this is a tremendous difference in dynamic range between the two. That's one use case. And could also be like things that falling off the truck, like you have in the US, these pickup trucks. People put their stuff in it and then they fall on the highway. So you need to detect small objects on the ground, basically, on the street. The other use case relates to environmental mapping. So you need to be able, with your radar, to have such precise capability to basically map your environment around you as you're moving. Maybe your GPS fails, you still have basically a sort of an extrapolated location, but more importantly, to really see where you are on the street so that you can position yourself in. And this translates to need for extended range capabilities, better detection, angular resolution especially, and also mapping that into processing and algorithmic capability to be able to separate and classify. This is a pole, this is an human, this is a kid on a trolley. And that's not something that is happening in one step. There is an evolution to it. So, and it started from the early days of around introduction of radar for automotives, around 90. We had this radar cube. I will talk about that a bit later, a bit more. So radar cube is, think about it as the way a sensor actually captures its environment. That is, the larger the cube, the longer the range. The larger the resolution of these small cubicles here, the more refined the space in the volume around you can be detected with a given SNR. In that cube, it started with being very coarse, 24 to 24.5 gigahertz band. These were the resources available 20 years ago, or 30. Being able to see a big car, that's it. Gallium arsenide type of systems, very discrete, very big, bulky, and very expensive. The big bang started moving to 79 gigahertz, so where spectral resources, so wavelength relates to velocity resolution, bandwidth relates to range resolution. So the cube potential was bigger. You can really achieve much more resolution. And in that, initially the step to 76 to 77 for long range, before the 76 to 81 for the complete thing, was implemented with also another major disruption, that was introduction of silicon technology, so silicon germanium. So that increased the available cube that you could achieve. But the real thing that actually brought a major transformation in the industry was the introduction of RF CMOS. We did that in NXP in 2010. That was the first RF CMOS chip, and when we went to our customers to show that, they simply would not believe it. They said, no, you're doing it wrong. There's something wrong. You cannot make with RF CMOS something where you need silicon germanium reliability and all that stuff. So that thing, introducing RF CMOS with a combination of what we call fast chirp waveform, allowed basically to span out multiple different use cases, long-range radar, short-range radar, corner radar, and especially because RF CMOS allowed to bridge the gap with high-performance CMOS microprocessors, allowing today to make one chips, SoCs. And that's really what really accelerated. Today, if a company is not on RF CMOS radar at 80 gigahertz, it's a company that will not exist for long. That's how disruptive that introduction was. But it doesn't stop there. So we're actually moving towards level 2, level 3 with RF CMOS and this type of systems, but we need to achieve more. And the question is how to expand resolution more. Do we need new technologies? Do we need to move to a different band to go maybe to 140 gigahertz? So that's really the interesting question. So what OEMs want is basically seamless scalability. Remember, OEMs, they are integrators. They take so many different technologies and they put them together. It needs to work as something that you don't experience as faulty. So when we give radars and chips, they all have to be integrated, and we're talking about multiple different radars. So front radars for urban pilots, corner radars to see around the corner, high-performance imaging radars to really map the environment and detect sensitive users, radars on the sidecars, you see a motorcycle passing you next to you, and rear radar, avoidance collision systems, or really detection of high-speed vehicles approaching you. This is where we are today. So NCAP regulations basically dictate what OEMs put on a car. That's it. There's a basic front range radar and 2 blind spot detection radars. Moving forward is the introduction of corner radars. And of course, there is a range aspect to it as gradual evolutions for corner radars to be able to detect a situation around the corners. Then we move into adding long-range radar and rear radar. So basically, the introduction of 360-degree sensing, and finally, imaging radar. Of course, this is happening in gradual steps in the industry, so it's not something you buy tomorrow. And this is gradually moving from very high expensive cars, step by step, into mainstream cars. So by 2030, market predictions are that practically 20% of the new cars sold will be on level 1. Having, of course, still a combination of radar, camera, and LiDAR systems. LiDAR 0, it's too expensive still. Moving to level 2 and level 2 plus, capturing practically 50% of the market of the new cars. And level 3 to level 5 cars, basically a mere 4%, which is something to be increased in the future. So a radar, I said aesthetics are important, needs to fit in a size of a core credit card, basically. An imaging radar, maybe make it a mobile phone. That's it. And the available resources you have is you have a spectral resources. Here is your wavelength. It's 76 to 81 gigahertz your band. And you have to operate within a 40 to 50 millisecond cycle because that's a safety aspect. That's it. That's your time, frequency, and resources in space. But you need to fit in systems that, as I said, they do 4D scanning. They have a flexible field of view. They are compact and low cost. They are able to deal with interference. If everybody has a radar on the street, then you can easily blast the radar of your fellow other rider or vehicle and simply jam it, and you have no detection. They need to be connected. And very importantly, they need to be safety. There is safety involved. There is reliability involved. They need to work for 10 years, 1 ppm. This is the target of automotive. In extreme conditions like 150 degrees Celsius. And so all that needs to fit in that small box without special liquid cooling and all that stuff. So now, in order to move a bit further into the deeper technologies, let me just spend a few words about the basic principles of radar. So the waveform typically used is what we call the frequency carrier wave modulated radar, FMCW, that's the keyword. So you have a transceiver here, it says a transmitter, typically quadrature, a PA, antenna, receiver, and what you do is you are transmitting a chirp. A chirp is a frequency modulated signal. It starts with a slow wave and it starts accelerating from, if you see it in a time frequency domain, it starts at F0 to F0 plus bandwidth. It can be 1 gigahertz, can be 4 gigahertz, can be anything. As you're transmitting it, it reaches a given range, it hits a target, comes back. It comes back, of course, with noise, attenuated, a bit distorted, and all that stuff. And you receive it. So you have a time delay. But now if you demodulate it here, the transmit signal as it evolves with the receive signal as you receive it, practically you will see that time difference translates to a frequency difference. That frequency difference is small. We talk about millimeter waves going to megahertz. So you actually come up with a tone here. This is a fixed. You have a fixed difference, a fixed linear chirp. You get a fixed difference, a tone. That tone, let's say it's 10 megahertz. It's here. And then you sample it. You sample it, and basically you can start processing it, because that is a detection of an object in range. And the other thing we do is by having it pulsed, it means we can separate the SNR, the longer the pulse, the better the SNR, from the bandwidth, which means the higher the bandwidth, the more refined the resolution. And if you have many pulses in sequence, you realize that as an object is moving, there is a Doppler effect deciding on the street when let's say, a police car is moving around. So that difference in small frequencies you can use from a chirp to a chirp to detect velocity. And then you add many of these components together, and you can detect angle of arrival. I will talk about that a bit later. So I mentioned fast chirp. So fast chirp, you could have 40 milliseconds, I mentioned, for a complete radar cycle. You take 20 milliseconds to detect, 20 milliseconds to do number crunching, processing. 20 milliseconds, you can have a very long pulse. Fine, that's the old-fashioned way. But you can have many small pulses. That's the fast chirp. It decouples one of RF noise issues with thermal noise issues. It decouples Doppler with range very effectively. It's very effective for multiple targets at the same time. It has redundancy. You lose a chirp, you don't care. You have the next one. So it gives a lot of extra redundancy in the system that you can actually use to make a much better sensor. So in the end of the day, you construct a cube. So you get your ADC output. You make a range FFT, just an FFT. You just want to detect the peak at which frequency bin it is. Frequency bin is a range bin. That's called range gauge here. But then I repeat many chirps, and I do Doppler FFT on top on its range bin. And then I come into the Doppler. For a given range bin, I have Doppler information. And if I have many channels next to each other to do beamforming, then I can also do angle of arrival estimation. And that makes the cube. The smaller the cubicle, the better the resolution. The larger the SNR per cube, the better the detection. So here is how it's usually looking like. This is a range, and this is a Doppler, and on vertically we have the SNR. If the SNR is high enough, we have a slicer. Beyond 15 dB SNR, there is detection. And then we create a target list. It's called a target list. But now how do we detect two objects if they are at the same distance? Remember, a radar sees the environment in a radial distance. So you cannot detect two objects in the same radius. So you need angle of arrival estimation. We can do beamforming techniques, so use multiple elements to detect the angle of arrival. It's a phased arrays is one example of it. Typical defense radars are operating this principle. The problem is you need high resolution. Therefore, remember, 1 sub-degree resolution means like 4 meters at 250 meters distance to detect two objects. So you need to go below 1 degree. And if you really make the math, 1 degree means 200 physical elements. That's a lot of elements that you need to operate simultaneously, put them in lambda over 2 spacing on a small area like a credit card. So, let alone the power dissipation. So something needs to be done for that, and the industry is using currently what we call coherent MIMO, multiple input, multiple output. What does this thing mean? You take 4 transmitters, you offset them, and you take multiple receivers, And basically, if and only if you're able to distinguish each transmitter individually on the receive side, you can actually multiply basically the different paths. So make a spatial convolution, because now the permutations around all these elements give you a virtual array, different distances on the receive side. But if you're able to detect the different individual contributions from the TX. So you need what we call orthogonality on the transmit waveforms. The good thing is that here I need 4 plus 4 physical elements. Here I have 8 achieved, 16. And if I want to scale it up to 2,000 elements, you realize the benefit is enormous. So virtual arrays, MIMO, is the path to really achieve efficient angle of arrival detection. How would it look like? You have a PCB here, a chip with 3TX, 4RX, patch array antennas, and then basically you have on the right side a virtual array that it's like implementing an antenna series of twice as large actually as you have on the left. But still the challenge is high because you still have a huge issue with power dissipation. The other point is that you have to find a way, as I said, to distinguish the different transmit waveforms. That's a key differentiation point of a radar. How do you do that? Multiple different ways. There is no single winner. Each one has pros and cons. You can actually start, let's say, take 4 transmitters and you switch on the first one, everything is switched off for the rest, then the second, then the third, and the fourth. That's fine, full orthogonality, it's simple, but you don't have 4 simultaneously transmitting, you have 1, so you lose 4 times the range. That's what you get. And you also lose 4 times the velocity, because you have to wait a long time before you get a second chirp of the same transmitter. Okay, so you can do something else. You can do frequency division. You transmit at different frequency offsets. That's also good, but you're compromising your baseband. You're compromising your range. Or you can do time difference. Same story. Another way is to start introducing coding. So I have my transmitter 1 with a different code modulated, transmitter 2 with a different code modulated, chip to chirp. That's called slow time CDMA. Or Doppler division multiplexing. Basically, we can multiplex in the Doppler domain, different small velocities offsets. That gives the benefit of transmitting simultaneously, but you compromise Doppler performance. And finally, you can do full CDMA. You just transmit code streams with excellent autocorrelation properties and excellent cross-correlation properties. That is, if you have 2 waveforms from different transmitters, they reject each other. They don't have a correlation. Easier said than done. You have issues with coexistence, with legacy of MCW, and a lot of interference. So part of the game is which waveform to use and how to make your hardware to actually make it. I mentioned RF CMOS performance, and what is so nice about RF CMOS performance? Well, first of all, you might have RF CMOS as a technology platform that actually doesn't have necessarily the best FTF-max that people working on millimeter waves typically associate with. But if you really think about it and look at plots like this, you will see that you can have much higher FTF-max. So this is red and blue is at 40 and 28 nanometer nodes representing Fmax and Ft. And here we see the current density. So I can bias method compared to a bipolar mass production type of millimeter wave process node here. So you can lack the maximum FTF-max, but you can get higher FTF-max if you bias the transistor at a low current density. Low current density means low power dissipation. The whole game in using RF CMOS is to find ways to save losses. That is, to find ways to simply eliminate how much signal you're losing. You don't need to generate 20 dBm signal and lose 5, just generate 16 and lose 1. And you have the game. And that is not only the device, you have to engineer the device, you fragment it, you combine it in an optimal way, you need to satisfy reliability constraints and all that stuff, which is a complete, let's say, expertise by itself. And also differentiate in the way you do the passives. Millimeter wave circuits are resonant circuits. So you have tanks, and you're losing a lot if you don't have the right inductor transformer. So by optimizing the way you do that geometrically, you can get substantially different quality factors. It's a factor of 2. This is an external vendor type of inductor. This is an internal optimized one with a given design process in mind. and also the way you do matching. So all these techniques you have to reconsider in a way that actually you reduce losses. Typical transmitter power efficiency on an automotive radar, best case 10%. 10% means for every watt I'm spending DC, I get 100 milliwatts of signal. So you have to really see that multiplication factor of 10. Remember how many transmitters I need. So saving energy, saving signal is essential. But you keep going. So you have RF CMOS, so you can do fancy stuff like calibrations. So I have a phased rotator. So here you see a 6-bit phased rotator changing the phase of a millimeter wave carrier with 5-6 degrees of resolution to make DDMA. But you can calibrate. So you don't need big devices. You can use RF CMOS to make small devices, therefore reduce losses. You don't need to generate one PA stage with 15 dBm. You can use power combining in the package, on the die, with smaller PAs. So all this interplay of let's say, approaches, you need to tune the design to the process and not do the same thing. Same thing on the baseband. You use a passive switch. CMOS technology is good for passive switches, for sampling, these type of things. And then you make a better converter, data converter, so you can recover your noise figure substantially. A very important point is chirp synthesis. You need to be able to make very fast chirps. And you cannot do fast chirps with a process and very low noise chirps. That doesn't give you 5 volts. So what do? You can use transformations. So we're making a PLL, for example, fractional PLL at 10 gigahertz, or you can use a thick oxide device. You use the redundancy of the process. You can use 2.5 volts, but then use multiple tanks, high performance, high bandwidth tank. And then you can start thinking, well, you know, I have a compressed signal. It's compressing full scale. That means it has a third harmonic inherent into it. Why don't I design a frequency multiplier, basically an impedance matching network with inductors, full passive, that tunes on the third harmonic. So suddenly I have a multiplication without spending the power for it. And then I can use another multiplication by simply forcing that into a transistor and having no linearity. So I do 2 multiplications without adding 1 over F noise. These type of transformations are essential in the way today we are making this type of high frequency and very fast chirp generators. But it moves further. You have a silicon, and silicon has good thermal diffusion properties. So here you see a temperature plot across the whole chip. It's 3 transmitters. You can see the hotspots here, and the temperature falling basically gradually around the transmitters. So good thermal properties of the process combined with good thermal properties of the package. So that means low thermal resistance. How much, if I have 1 watt, to how many degrees does it translate in the external world? That's essential. So you need EWB technologies, flip chip technologies, and also by making things smaller, it means that you don't have all this extra need for underfill device for reliability, board level reliability cracks. So keep things small. And that means you keep also losses small. You put all these things together, and then you come to a chip like this. This is an SoC example from NXP. We just released that. It's the flagship product at the moment of our radar business. I started working on this one 5 years ago. That's the time it takes to really have a product cycle in automotive. Once you do your research homework beforehand. It consists of 4 transmitters and 4 receivers. It has multiple different processors for safe computing, so ARM Cortex, M7. It has a specialized radar signal processing toolbox. You give that to tier 1, they can program whatever fancy algorithms they want. Multiple different interfaces, and also, of course, a hardware security engine and functional safety engine. So that's how it looks like. It's as big as, said, 5 by 5 centimeters if you put in a sensor. You see here the patch antenna array, and the chip is actually back here. It's not visible, and you can see actually how the chip looks like on a finger. So it has a very small chip and a bit larger sensor to it. Now, this is the thing I showed you on the left side, but there is more you can do at the antenna level to make things better. When one of these emerging technologies in the field is called waveguide antennas, 3D waveguide antennas. So what you do is, you realize that the patch antenna is an antenna of several centimeters that has many losses. It couples next to each other. a loss on a PCB means I need to use an RF expensive material like Rogers 3003. So you make an imaging radar with many of these things, the cost is enormous, the space is enormous. So why don't you simply do waveguides? Waveguides means low loss, zero loss. To do that, you need a specialized antenna, but you also need to be able to launch the wave directly from the die into the waveguide. So nothing in between. So that's the construction we have here. We have the die, it's a flip chip. You go through a substrate of the package, it's a flip chip package, and directly you radiate through a hole in the PCB here where the antenna is. It's a 3D printed antenna, and you can see it here. We did that with Huber & Schuner, is a partner of ours specialized on antenna technology. The benefit is enormous. It's around 11 to 12 dB of SNR improvement. You do nothing on the chip, you just improve your antenna, you get better directivity, you lose the losses, you have less power consumption, and basically you get a much longer range. So here with experiments, you can see detecting motorcycle approximately up to 400 meters compared to 200 meters without this antenna. So that's how important the antenna is, and that's the trend basically. You can do more by integrating the antenna on the die. You can do, for example, what we call artificial dielectric structures. So you have your die, you radiate through an opening, and you use the metal stack of your package. You put some small metal patches in a given specific way, and with that you can bend the wave and radiate on a given angle. So that's what you see here for azimuth and for elevation. The difficulty here is that you cannot scale that up in a package. So this is not picking up yet at the 80 GHz band, but it is essential for moving at high frequencies. But still is a capability that one needs to explore. Imaging radar. So let's take what is it? Let's see on the left the 3x4 system I showed you before. Basically, you have 12 degrees of resolution. So this is my colleague Feike. We did an experiment, so we're just like 5-meter range or a bit more. And you can see a detection here. This spot is a detection. Remember the high SNR slicer, this is a confirmed detection, but you don't have the resolution to really see anything further. But if you use 192 elements for 4 of these chips in cascade, practically you can have 2 degrees of resolution. And then you can start seeing detections in the arms, detections on the waist being separated. So you can start thinking, hey, I can make classification here. This might be a human. And this is why you need to have so much better resolution. Typical numbers, mainstream, or not mainstream, but actually highly optimized MIMO systems, around 200. Some peak in numbers is 2024, Arbor systems, for example, in number of channels. And a lot of high processing computing. Optimized MIMO means we are exploiting architectural redundancy. Therefore, we use, let's assume we want to reduce the number of channels to save power. So instead of using brute force 2,000 channels, I can use 192 channels, but then start overlaying at a sensor level different fields of view, like here. I have a system with 3 different antennas. I use a lot of directivity, and I overlay them. So the fact that I have common fields of view gives me ability to solve ambiguities. I'm interleaving different type of chips. And that combination, you see here 4 cascaded chips synchronized, waveguide launchers on the PCB here. So that's the board, through a stabilization port here onto the antenna, and on the bottom the complete macro procession. This is a box, yeah, around as big as a mobile phone. And that's the way basically to reduce also the number of channels without needing to resort to really huge physical arrays. With that, we made the video you've seen in the beginning. So this is a more elegant imaging radar system consisting of indeed 4 cascaded chips using our latest transceiver chip. And I want to show you a little bit, a small video now on how it looks like in detection real life or imaging. So let's go to see that one. Oh, it plays very well. So you can see here at the bottom how the radar practically sees the environment as it moves. And at the bottom you see the objects. So you will see the curves of the road. You will see actually different bushes or trees here on the left side. And so you will see also some vehicles approaching. So the car has a 360-degree cocoon, so corner radars, imaging radars. So it can really detect all things happening around it. And if your eyes is sharp, soon you will see also the bubble and the field of view, but it's very difficult to see that from here. So now there's a car approaching from the back. You start seeing the detections, and you see the more it approximates, it comes closer. You will start seeing that there's another car just crossed by. And that's what we typically call imaging, mapping around the environment. So you see that car coming back on the backside here. You see the detection list increasing, more hits. It's a very typical thing for radar. You cannot see the whole thing. You just see multiple spots around it. And that you need to put in an AI engine and a classification engine to really, make up a certain certainty that this is okay. So I hope you get a little bit of a picture. I think here is visible the field of view, that gray part, how this thing looks like in real practice. An important point to mention is the radar interference. It is a topic heavily been discussed. It's a topic that requires a lot of attention because you have so many devices, one jamming the other and all that stuff. So what happens in practice is you have a chirp. This is the blue thing here, the blue line. You have a delayed chirp, that's your target. If you demodulate, it's coherent. You see this black line here that you're sampling. But if you get another radar crossing by, it could be an arbitrary slope, an arbitrary delay, you just don't know anything about it, and not coherent. So when you demodulate it, because you don't convert it with your own reference, you will see just a burst. If the frequency difference is large, then it's out of frequency, you filter it. But if it isn't, the part it isn't, that really jumps your radar. And you can see it in a range Doppler plot. So here is the detection, and this is what you see, basically another object interfering. There are multiple approaches to mitigate that. Random chirps, a compass method, that is, you have a rear radar and a front radar, they have different polarization. Or you're changing the way your radar emits in different bands as you're turning. So it's really different angles, different sub-frequencies. And finally, band regulation. But nobody wants to do that so far because waveform is a differentiation feature. It's not like communication where you have a standard. There is no standard. You have a band and how much you're allowed to emit. You do whatever you want in it. And that's how they're making their money in let's say, in a tier 1 level. Last part, coming to the end, is, well, there will be a point where we use the best of technologies, we use the best of ideas to bridge the innovation gap of where we're at today to how much this 76 to 81 gigahertz band allows us to do in such space and with this time. And there is no more to do there. What then? Well, we can go to higher frequencies. We've done that before. We went from 24 to 76, and we live in an evolution of 20 years now, maybe another 10 or 20. So we can go to sub-terahertz imaging, or before that even, to 100 to 300 gigahertz radars. Very refined resolution, small cubes. We can even move to optical LiDAR, as I said. These are things we're exploring. These are real demonstrators. How to make it small, that's the big bet. But also there are new opportunities, joint sensing and communication, augmented automotive safety, meaning that you have use cases, you have base stations, poles, etc., giving to the car a sensing capability, but through augmenting. That is, you get buildings with sensors, they sense the situation, send it as a message on the car. So many use cases that actually come up, and this is just how a typical of these beamformer chips could look like. This is a 6G demonstrator we have in the company. Will be demonstrated in the Congress with Ericsson in a few years. You need to do a lot of things to get there. First of all, yeah, it's not easy to generate signal power, so you need a wireless optimized technology. CMOS might not be enough, you need something else. How to do that? Will it be FinFET? I don't think so, because you cannot generate, but you need FinFET for mixed signal performance. Will it be FD-SOI? Maybe. Maybe, however, you can use indium phosphide to get really 900 gigahertz of FT-Safe Max, and you can use a scaling of BiCMOS technology. How to radiate effectively? I said, no money in the middle. You cannot go to a strip line anymore 140. You lose all your signal just going through a ball, a copper pillar or a ball from the die to the PCB. Forget it. You need to radiate from the chip somehow and use directivity. So we go to focal planares, lenses, millimeter wave lenses, how to do that to connect it to the chip. Heterogeneous integration. Well, I cannot do everything with one node, so why don't I split in chiplets? Well, I can do different things in different nodes. And then I also start butting different wafers on wafers, so I can do my SIGI for long range power amplifiers, but I can do my mixed signal data converters and beamformers on FD-SOI, for example. And finally, there's an explosion of data processing. There is more channels, more effects, more processing needed, higher resolution. So in the end, how do you deal with all that? You need, the 5 nanometer processors, you need the 2 nanometer, you need carbon nanotubes. It's a big thing. So it's a big explosion that forces you to start thinking, maybe I should simply exploit the redundancy of inference. A radar is a system with inference. It's not a communication transmitting bits per second, information fixed. It's something might happen, and for the rest, I'm burning power for nothing. So these are the type of different paradigms that actually are at the moment currently explored. And with that, I come to my summary. So millimeter wave automotive radar is evolving towards 5-level automation. The market is growing strongly, and there's a lot to do there. Innovation is the driving force behind that. Introduction of new processes, new architectures, advanced packaging. And as I said, this will keep us going for quite a long time still. There are fundamental barriers, boundaries. The moment we start getting close to that, we need to consider shifting to a new node. It's only a matter of question of when rather than if. And finally, when we do that step, I think from moving everything to an SoC and all this CMOS integration direction we had for many years, we now move into a new paradigm also with the packaging platform becoming the cauldron of innovation where everything is coming together. With that, I conclude. Thank you for your attention.